in item A, we derived a tensor belong to the three-dimensional space using the extrinsic geometry. Now, in this B here, okay, the part in this case, we will study the intrinsic geometry and the tools for this intrinsic geometry, which is the exterior algebra. In this case, in the three-dimensional space. You see, in the development of this study, is a lot of videos for you to understand clearly, okay, about the intrinsic geometry and exterior algebra. You see, you can extend for any dimensional space. Okay? That's an important consideration. Okay, today is March 29th, 2025. Now, let's introduce some concept about the intrinsic geometry, just for you to understand what really it means. Now, intrinsic geometry is a way of describing geometric properties that depend only on measurement made, attention now, made within a given space without reference to an external embedding. You see, I'll show you an example for you to understand this clearly. So, this concept is crucial in differential geometry, where use in this case, okay, where we study the space such as surface or manifold. Manifold is related to the intrinsic geometry. Now, these are based solely on information available within the space itself. You see, the exterior does not enter to play this game over here. So the exterior is related, the exterior space is related to exterior, in this case, is extrinsic geometry. Intrinsic geometry, I said here, okay? So the external, okay, is not considered. Only in this case, or the surface, or a line, or a volume. So this is, for example, on a surface like a sphere. Intrinsic geometry always allows us, okay, to define distance, angles, and curvature without needing to refer to the three-dimensional space, in this case, in which the sphere is embedded. Oh, I brought here a papaya, okay? This is geometry, okay? You have this exterior space, is not considered. So you have a point on the surface, and I construct a plane, a tangent plane to this surface at this point. Okay, this tangent plane, this space, doesn't have nothing to do with another point and another tangent plane. So there are many as you want, okay, tangent plane related to a surface, okay? Each point is independent what is happening on its neighbor, okay? That's a trick to understand, to start understand the concept of, in this case, intrinsic geometry. So this is said here, but it's good for you to understand. So you eliminate the external space from this study about intrinsic geometry. Okay? Now, it's important here, I gave an example of the papaya, okay? The same on the sphere in the three-dimensional space. So, In this case, if the example uses sphere, okay, the sphere is embedded on this space outside, okay, the external space. That's intrinsic geometry. Again, it's the focus of the intrinsic geometry is not the external space. It is a tangent plane. In this case of a surface, is a tangent plane that we create at each point on the surface. Okay? That's why it's called intrinsic geometry. Now, in this case, okay, you see, in this case, without needing to refer to the three-dimensional space in which the sphere, in this case the papaya, is embedded. Okay? This is a foundation of the Riemannian geometry, where we use the attention now, okay, on A, part 1 to 7, I said clearly that the importance of the metric. Here, only the metric plays this game over here. No position vector, you see, no vector, no. This is out of our study. It's just the metric Gij, in this case covariant, or Gij contravariant. That's clear here. This is called Riemannian geometry. Now, you remember from A, extrinsic geometry, I just remind you there that Gij is related to measure distance and angles directly from the coordinate system attentional. Define all the space. Attentional. In this case, okay, the geometry defined on this plane over here, this tangent plane. Okay, the concept there is completely different if I take another point, there are another space. Okay, that we call the set of all this tangent plane. We call a tangent bundle. Okay, that's it's good for you to get clearly all this concept. Now, mathematically, intrinsic geometry relies on attention now here. This is I emphasized, okay, in this case from part 1 to 7. That's why it's worthwhile for you to go back and study deeply, okay, part 1 to 7. Then, mathematically, intrinsic geometry relies on metric tensor. This is covariant metric tensor or the contravariant metric tensor, okay, which define distance and angles. No position vector here. No position vector. Second, Christoffel symbol. We derive the Christoffel symbol in terms, do you remember, of the metric. See? Christoffel symbol, in this case of second kind, was derived, okay, in terms of the metric. So metric, and the Christoffel symbol, they are responsible. Okay? In this case, you see a tensor, not a scalar. Scalar is a zero-order tensor. I'm talking vectors, second-order tensor, and so on. So the meaning, okay, the Christoffel symbol, they describe how change direction when moved along a curve. So if you have a curve here, if you have a curve, see, at each point, okay, we will have a different Christoffel symbol. That's why, because at each point we have different metric tensor. It's clear now, okay? Forget, I'm repeating, okay? forget the space outside this, in this case, the surface here of the papaya. Okay? Now, the third, curvature Riemann, we didn't derive this. This is a curvature Riemann tensor. Okay? Here you have 4 free indices over here. I, J, K, L. We'll derive this. Okay? Now, what does the remainder, the curvature, okay? They measure how much the space bends, in this case, intrinsically. Okay? So the Riemannian curvature, for instance, at this point is completely different of Riemannian curvature at that point. You see, this I have one curvature, here I have another curvature. That's important. Okay? And okay, what is the tool, okay, to analyze all this concept? The tool is called, in this case, exterior algebra. Exterior algebra, also called Grassmann algebra, is a mathematical framework used to describe objects that generalize vectors such as length, areas, volume, and higher dimensional concepts in a coordinate free, this case, in a coordinate free manner. Okay? It plays a central role in a differential geometry. You see this differential geometry, I based one word called form, F-O-R-M. I'm not explaining what it is now. So, I guarantee you, okay,